Hey guys, welcome to video 60. Today we're going to start talking about vacuum tube triodes. Let's begin with a real quick review of the diode operation we discussed in the previous two videos. We have a evacuated glass envelope, we call it a tube. Internally we've got a metal plate we call the anode and another plate called the cathode. We heat the cathode with a filament which creates a cloud of electrons around the cathode that's called the space charge region. And when we forward bias the diode, that is, we make the anode positive with respect to the cathode, we're going to get flow of electrons from the cathode to the anode, and that constitutes our anode current. The anode current is described by the Child-Langmuir law, which says it's equal to K, the perviance of the diode, times the anode to cathode voltage raised to the 3/2 power. Now if we take our vacuum tube diode and we insert a fine wire mesh in between the anode and cathode, run a terminal to it, we'll call this the grid terminal, we get a vacuum tube triode. And a triode can be used as an amplifying device just like a bipolar transistor or a field effect transistor. And the equation that describes the plate current as a function of the grid to cathode voltage is I sub P is approximately equal to K, the perviance, times the grid voltage plus the plate voltage divided by mu raised to the 3/2 power. So it's a modified version of the Child-Langmuir law. Now, mu is what's called the amplification factor for the triode, and this is basically the maximum possible voltage gain that the triode can have. It's a fundamental triode parameter. Now, as you probably surmised already, the triode is a normally on device just like a JFET or a depletion mode MOSFET. And although FETs are square law devices, triodes are 3/2 law devices. All right, so they're going to have a little bit different transfer characteristics and distortion characteristics, but that's a topic we'll talk about later. And again, mu is the maximum voltage gain that can be exhibited by the triode. We'll talk more about that later. We can get a kind of intuitive idea how the triode works by looking at these three schematics over here on the right. In the first case, I'm applying no voltage to the grid of the tube, so VGK equals 0. And if we apply an external plate voltage VP, we're going to get electron flow from cathode to plate, and we get a large plate current that would be given approximately by this equation. All right, if we apply a negative voltage to the gate with respect to the cathode, that is V sub G is less than 0 volts, but not very big, we're going to tend to decrease the plate current, assuming that the plate voltage is constant, and that's because the negative potential on the gate is repelling the electrons from the cathode and reducing the overall electron flow from cathode to plate internally. Finally, if we apply a large enough negative voltage to the grid with respect to the cathode, we can turn off the internal current flow completely, and we've reduced the plate current to 0. Okay, let's take a look at the characteristic curves that describe the triode. Over here on the left-hand side of this page is the circuit we'd use to generate the device curves. And the first set of curves we're going to look at is this family of transconductance curves for the triode. This is a graph of plate current versus grid voltage for fixed values of plate voltage. And technically, I'd prefer to be more precise and call this V sub GK, the grid to cathode voltage, but the tube data sheets just call it V sub G, so that's what I'm going to go with here. Now, the second set of curves we see is what's called the plate characteristic curves for the triode. This is a graph of plate current versus plate voltage, and again, I'd prefer to use V sub PK, the plate to cathode voltage, but the data sheets use VP, so that's what I'm going to stick with here as well. Now, coming back over to the transconductance curves, ideally these curves would be described by this modified Child-Langmuir law equation, but in reality, it's more complicated than that, and this is really only a rough approximation that we can use to describe the shape of these curves. I'll show you that in a few minutes more precisely, but for now, we'll just assume that this is an accurate equation to characterize these curves. Now, one thing that you will notice is that the transconductance of the triode is pretty sensitive to plate to cathode voltage. If we compare these to the curves for an N-channel JFET, for example, we see that we only use one curve to represent the JFET. We don't have a family of curves here because the JFET and the depletion mode MOSFET, for that matter, are not very sensitive to changes in drain to source voltage. And that's not the case for the triode. Again, these curves are very sensitive to plate to cathode voltage. And also remember that the curve for the JFET or the depletion MOSFET is a square law curve versus the 3/2 power law curve for the triode. Okay, now let's go on over to our plate characteristic curves again for a minute here, and notice that these curves don't go up and level off at some particular plate current value like a bipolar transistor or field effect transistor might. They just keep increasing roughly according to the 3/2 power law. And remember, this equation doesn't describe these curves. There's no simple equation that I know of that describes these. We're going to handle analysis and design graphically. But anyway, for comparison purposes, let's again look at the drain curves for a field effect transistor in comparison and notice that they are quite different. Okay, let's get rid of these drain curves and we're going to go over and take a look at an actual triode. In this case, we're going to look at the 12AU7 or ECC82, and there are also a bunch of other equivalent tubes, but we'll talk about that later. This is a medium mu dual triode. We have two triodes in one tube, and here's the pinout. Now, notice that there is one heating filament for both cathodes. The heater is connected end to end from pin 4 to pin 5, and there's also a center tap that goes to pin 9. So we can operate this filament either from 12.6 volts across pins 4 and 5, or we can connect the ends 4 and 5 together and power it from the center tap to the ends using 6.3 volts, and that's probably the most common way that we're going to power this tube up. Down here below we see the typical representation we'd find on a schematic diagram, and over here on the right we've got the transconductance curves for the 12AU7. Okay, I thought just for the heck of it I'd take a second here and show you some of the results I got trying to curve fit the triode equation to the actual device curves for the 12AU7, and pretty much no matter how I manipulated the parameters, it really didn't get any better than this. So obviously there are some other factors or terms missing that I'd need to account for, but maybe I can do that in some future video. But for now, we're just going to rely on graphical analysis approaches using the actual device curves. Okay, now let's go on over and take a look at the plate curves for the 12AU7. The curves we're looking at here were taken from the General Electric datasheet for the 12AU7, and one of the first things you notice is that they really divide this thing up into very fine gradations. On the horizontal axis, each of these minor divisions is worth 5 volts, and on the vertical axis, each minor division is worth 0.5 milliamps. So even though we're doing graphical analysis and design on these curves, we can get pretty precise results. All right, now we see the plate current versus plate voltage for a number of different grid voltages, starting with grid voltage of 0 volts all the way through a grid voltage of minus 30 volts. And this curve that's intersecting most of the plate curves is what's called the maximum power dissipation hyperbola for the diodes. Basically, this is a graph of a constant power 2.75 watts, which is the maximum plate dissipation for the 12AU7. We can locate our operating point anywhere underneath this curve, and our load line can extend anywhere underneath this curve as well. We don't want to operate anywhere above it. That can damage the tube. Now, as far as analysis and design goes, we're going to be using the plate curves a lot more than the transconductance curves. So these are the ones we're primarily going to be working with. All right, now before we wrap up this video, I just want to take a quick look at the small signal parameters for the 12AU7. And so let's go down to this next slide. And here we've got the typical small signal model that I'm going to use for the triode. There are two possibilities. We could represent it either as a voltage controlled current source or a voltage controlled voltage source. I prefer to go with the voltage controlled current source because that matches up more closely with the field effect transistor models that we've used previously. Now, it's pretty easy to see the similarity between this model and that of the field effect transistor. The grid to cathode resistance is essentially infinite. The plate current is equal to the transconductance times the grid to cathode voltage. That's just like GM times VGS. And we've got little r sub p, that's the dynamic plate resistance, which is equivalent to the internal resistance of this current source. Now, recall we talked about the parameter mu for the triode. That's the maximum available voltage gain for this device. And from the curves, it's equal to the derivative of plate voltage with respect to grid voltage, or plate to cathode voltage with respect to grid to cathode voltage. The transconductance of the 12AU7, or any other triode for that matter, is derivative of plate current with respect to grid voltage, and we could get that by determining the slope of our operating point on whichever curve we're using here. And finally, the dynamic plate resistance is the derivative of plate voltage with respect to plate current. Now, all these parameters are listed on the data sheet, and if I call up the 12AU data sheet for a second here, we see that, say for a plate voltage of 100 volts, the typical mu is 20. Our typical plate resistance is around 6.5 k ohms, and the transconductance is 3100 micromhos, or 3.1 millimhos. At a plate voltage of 250 volts, we've got a typical mu of 17, a plate resistance typically 7.7 k ohms, and a transconductance of 2200 micromhos, or 2.2 millimhos. Now, note that they're listing this as plate voltage. Normally, we're really going to be looking at plate to cathode voltage, but again, these old data sheets use some conventions that would be considered odd by modern standards. When you compare a tube data sheet to a transistor or FET or integrated circuit data sheet, things are a little bit difficult to interpret sometimes. But in any case, these are the typical values for the 12AU7 used as a Class A or a Class A1 amplifier. And we'll talk more about this later when we actually design amplifiers. Okay, now back to our parameters. We can relate mu, transconductance, and plate resistance sort of like we do with Ohm's law. Mu equals GM times RP. And notice that dimensionally this works out right because we've got volts over volts for mu, which is dimensionless. And here we've got mhos times ohms, which cancels out to be dimensionless as well. And the transconductance is mu divided by the plate resistance. Plate resistance is mu over GM. And these are all fundamental parameter relationships that we'll use when we design and analyze amplifiers using triodes. Now, I just want to mention that normally when we're designing or analyzing amplifier circuits using triodes, we're going to just use the parameters given on the data sheet. That is, we'll assume mu is 20 or whatever and just go from there. Now, there may be times when we'd want to determine these parameters from the curves, and what we would do in that case is find our Q point wherever it is on either this graph or this graph and determine our parameters based on changes in, say, plate current versus grid voltage, and determining these parameters for our particular Q point. But again, most of the time we'll just use the values given on the data sheets, and that'll work out just fine. Now, that's going to conclude today's video. In the next video, we're going to analyze and design some triode circuits just from a biasing standpoint. We're going to bias them up for whatever Q point we desire, and we're going to analyze some circuits and determine what their Q points are as well. And I'll build some of these circuits and show the experimental results, and we'll see how well our theoretical calculations match up. But that's for the next video, and I'll see you guys next time around.